So this is a short lesson on how to find the inverse of 2 by 2 matrix, which is not hard, and it does help us in that we can work through some examples involving matrix inverses. If you're curious about the process for inverting larger matrices, it's in chapter 15 of Essential Mathematics for Economic Analysis. You could find it lots of places. It's, as I said before, not particularly hard, but it is pretty tedious. But 2 by 2s, no problem. So let's start with a 2 by 2 matrix. Rather than using the subscripts, I think let's give the elements different letters. Okay, so there's our matrix. Here's the formula for the inverse of a 2 by 2 matrix. A inverse is 1 over AD minus BC times D negative B negative C A. Okay, so what do we do to find the inverse? First, we take the on diagonal elements, A and D, multiply them, and we subtract off the off diagonal or the opposite diagonal, the southwest to northeast elements. Okay, so this is a number that we get. And since I'll mention it later, I'll just tell you now that number has other uses. It's called a determinant. This is the spell it right. Well, so it's the determinant. Okay, it's just the denominator there. So AD minus BC is the determinant of A. Put that in the denominator of the fraction. And then to the matrix itself, what we do is we switch the positions of the on diagonal elements. So we put D where A had been and A where D had been. And we leave the off diagonals where they are, but we change their signs. Not super intuitive, but it works. So let's check to see if it works. If it works and we take A inverse times A, we should get I. Okay, so A inverse here is 1 over D minus BC times DA negative B negative C. So I'm just copying my A inverse here and pre-multiplying A by that, or post-multiplying it by A if you want to say it that way. It's my A, B, C, D. Okay, so keeping that 1 over the determinant out on its own for a minute, it's 1 over AD minus BC. And now let's do the matrix multiplication here. So they're both 2 by 2, they're conformable. I get DA minus BC for the 1, 1 element. I get DB minus BD for the 2, 1. I get negative CA plus AC for the 2, 1 element. And I get negative CA wait, sorry, I lost my place there. I got the 2, 1 element by multiplying the second row of the lead and the first column of the lag. And now for the 2, 2 element, I need the second row of the lead and the second column of the lag. And that is negative C times B. It's looking in the wrong place there. Negative CB plus A times D. Okay, let's pretty that up. 1 over AD minus BC, DA minus BC. DB minus BD is 0, and so is negative CA plus AC. And now when we go through and do the scalar multiplication, we see that we do indeed get 1, 0, 0, 1 here, that we've just got AD minus BC written a slightly different way here and here, but the formula did work. We did get back to the identity matrix, which is what the inverse should do. Okay, so that is the process. It works. We just proved that it works for a 2x2 matrix. We will see in the workshop for this unit, we'll use this in a regression example. As I mentioned, you might encounter determinants in other contexts. Determinants are a big part of the process of finding matrix inverses. If you're going to invert a larger matrix by hand, you'll find yourself calculating lots and lots of determinants of various submatrices and moving them around. You can calculate determinants for any square matrix. Calculating them for a 2x2 matrix is easy in the sum process that I just mentioned. It's the on diagonals minus the off diagonals. There's a slightly more complicated formula for doing it for a 3x3. If you're interested, it's called Sarris's rule. Again, you can look it up in the book, but I don't think you have that many occasions where you're gonna, possibly any occasions at all, where you're gonna use that. And calculating determinants of 4x4 matrices is not as awful as calculating an inverse, but it's still pretty tedious. And again, something that you will probably always be asking a computer to do. But knowing that a determinant is a number that you get from putting together the elements of a square matrix in a particular way is helpful. They do show up in other contexts. For us, the most important use of a determinant is that it lets us know whether a matrix is invertible or not. So let's just even write that out. Square matrix is invertible if square matrix A is invertible, if the determinant of A does not equal 0. Okay, so that's a separate point. Let me go back to what we were doing before, and you can see that if this determinant was 0, that would be bad news. We wouldn't be able to put it in the denominator. We couldn't calculate it. The determinants of larger matrices come from a more complicated formula, but it's still true that if they equal 0, you can't calculate the inverse. It means that matrix doesn't have an inverse there. And it is actually also true that the inverse of the matrix, of any matrix, is the determinant multiplied by a matrix that you get by rearranging and recalculating the elements of the existing matrix. But this is an important point. So if you're thinking about when inverses exist, first thing to think about is the matrix square or not? If the matrix is not square, you know the inverse doesn't exist. Don't even worry about it. If it is square, the question is the determinant 0 or not? If the determinant is non-zero and it's square, then you can calculate that inverse. Okay, then it exists. If the determinant is 0, the matrix is not invertible. And that's enough know-how for finding inverses and finding determinants to allow you to work through some 2x2 examples. So that's where we're going.